projector's on, and it's yeah, it is on. Yeah. On which screen? Yeah, it's got it's. It seems yeah. You're yeah. I can see what you're doing here. Yeah. Yeah, that's working now. I think. It's not project. Yeah, it's projecting it now. That's fine. Okay. Everything's good now. Okay. Thanks very much. Thanks. Thanks. Bye. Bye. right. Okay, it's good to see you guys again. Can I just check, do you think this is okay to start, or are there still people coming in? Don't know. Okay. Okay, we'll give it a go and see how we go. All right. At this stage, I think you guys probably know as much about X-ray production as I do. You know, if you're asked to draw the X-ray tube, you'll be able to do that. If you're asked to talk about the function of the filament, you can do that. If you're asked to talk about the anode, you can do that. If you want to talk about the interactions of electrons with the anode, you can do that. You can talk about the slope of the anode, and you can talk about geometric unsharpness and the focal spot size. So you should be okay with all those things. If you're not, come back to me and we can find tutorials and so on to cover these things. We've almost finished this lecture. What I intend to do today is finish this lecture and then move on to doses. At this stage, you will be starting to see that there are a plethora of dose units. There are things like Curies, Becquerels, Grays, Sieverts, Rads, Röntgens, Rems, and so on, okay? I will steer you through all of those, and by the end of today, and hopefully we will have enough time, you will have a complete understanding of which dose units are relevant to you and exactly what they mean. Okay. The last thing we talked about was filtration. And in particular, I made you draw that graph, which I would urge you to draw and draw again, you know, to make sure you understand it. The graph that demonstrated bremsstrahlung with characteristic radiation, and then we showed you the impact of non-selective filtration on that curve. And in particular, we showed how the intensity reduced with filtration, with non-selective filtration. I'll come back to that term in a minute. How the intensity reduced, but how the average energy increased with increasing filtration. That's good because it lowers dose. We are obliged to have filtration. We have to have it. You know, there are legal requirements that we need 2.5 millimeters of aluminium equivalent. Remember that term? We talked about aluminium equivalent. We need 2.5 millimeters of aluminium equivalent. Inherent filtration doesn't do that, so we've got to add filtration. And in particular, we usually add things like sheets of aluminium or copper into the beam to achieve the level of filtration. Now, just coming back to that term, non-selective filtration. By non-selective, I mean that it's a bit of a crude tool. And in particular, I'm talking about aluminium and copper. They are the two filters you're going to come across time and time again. Aluminium is going to be the main filter you're going to come across. You're going to see aluminium almost in every X-ray tube you come across. And occasionally you'll see copper, particularly in pediatric units. Copper is better at filtering the beam. The downside of copper, however, is because it's better at filtering the beam, your average energy is going to increase more. What happens to image quality when the average energy increases? Contrast decreases. And you see that time and time again. If you put the same thickness of aluminium into a beam, the same thickness of copper into a beam, the copper will reduce the soft radiation much more effectively. But the impact on contrast will be apparent. So remember that. People will revisit that time and time again and get it wrong. Increased energy of the X-ray beam reduces image contrast. Okay. Now, and as I say, the non-selective filters simply, you know, like anything, they get in the way of the X-ray beam. You simply stick them into the X-ray beam, they get in the way of the X-ray beam, and as a result of that, they stop some X-rays. They're not very clever, they just stop the X-rays, okay? And particularly, you can imagine they're going to stop those X-rays that have the lower energies. The high energy X-rays will probably still keep going through, unless you've got loads of filter. but generally it'll stop the lower energy X-rays. Now what I want to talk about, and why I stopped here the last day, is that this is a concept that I think you should understand. It's a completely underutilized thing, and it's called a K-edge filter. Now, the name itself suggests to you that it's doing something around the K-edge of the K-edge of the material is important. Okay. Now, what I want you to do, and it works with higher atomic number materials, and particularly it works, I'll give you an example of a material, and that is erbium. We've done some work with erbium before. If you want to see an erbium filter, I have one in my office. And we've done I had a PhD student in Dublin who demonstrated that erbium did filter the X-ray beam, no better than aluminium in terms of dose, but in terms of image quality was much better. And this is why I want to impress this onto you, these K-edge materials. It may not be any better than aluminium or copper in terms of dose, but it will be better in terms of image quality if it's used correctly. Why isn't it used all the time then? And Louise Rainford, who's now a professor of medical imaging in Dublin, her PhD demonstrated this quite clearly, and the question was asked, well, why don't we use erbium? Erbium probably costs about $1,000 to $2,000 for a filter, whereas aluminium may cost about $1. And this is the reason why. But if you think of the hundreds of thousands we pay for other pieces of equipment, it does seem $2,000 doesn't seem to be excessive. But anyway, let's go back to the physics. All right. So, if you had a filter, okay, and on the y-axis we say transmission of X-rays, how many X-rays are going to get through this filter? And on the x-axis, we say energy of X-rays. Okay, so it's simple enough. You've got a filter. Okay. This filter has remained constant. Okay, we are not changing the filter. The energy of the X-rays, however, is increasing. How does that affect the X-rays getting through? How many X-rays will be allowed through as energy increases for this filter? Okay. So I want you to draw the graph. Okay. Yeah. It's dead straightforward. So as energy increases, how will transmission of the X-rays? Yep, that's it. You're under pressure. Okay, so simply, if you increase the energy, I've seen a lot of blank, this should be fairly straightforward. If you increase the energy, will you get more or less X-rays going through? Yeah, good, that's right. Well done. It's the other way, transmission, yeah. If you increase the energy, more of the X-rays are actually going to go through. I'm seeing, it's probably a little early on a Tuesday morning, I'm seeing a lot of blank graphs, that's right, well done. No, it will be linear, you won't see a sort of a dip, okay. Yep. Yeah, you won't see that. Normally, with normal filters, you won't see that. Unless you're being extra clever about what I'm going to say in a minute. Okay. Let's see, what have you guys done? Yep, well done. Yep. Okay, good. Most of you have this. It's not a trick. It's simply, if you've got more energy, if you can imagine if I used an energy of, say, 3 kV, okay, and then I used an energy of 100 kV, you're going to get more X-rays passing through this with 100 keV. As energy goes up, transmission goes up. Okay, simple thing. Some of you are doing rather clever curves, but that at this stage is all we want to see. Okay. Now, the ones who are doing the clever curves, I'm not sure if they are clever or wrong, but because what I'm going to talk about next will actually, some of those curves will actually fit what I'm about to say. Okay, that's what you'd expect, and that's how aluminium works, that's how copper works, that's how non-selective filters work. Okay. Now, let's just explain how the K-edge filters work. K-edge, first thing to note about K-edge is that they are higher atomic number materials. Okay. One such material is erbium. I can't remember the atomic number of it. Does anyone know the atomic number of erbium? Yeah. What is it? 68. Well done, 68. Okay. And it has a K-edge of 57.5. Okay. Okay. It has a K-edge of 57.5. Okay. Sorry, what's the K-edge? 57.5. What is the K-edge? K-edge, so it's the binding energy of the inner shell electron. Okay, remember the K-edge electrons? So the K-edge is the energy required to remove an electron from its inner shell. Okay. So, tell me what's going to happen. If an X-ray coming in interacts with this erbium and it has an energy of 30 keV. Okay? Remember the K-edge is 57.5 keV for erbium. If the energy of the X-ray have 30 keV, what will happen when that X-ray interacts with that K-shell electron? Nothing. Well done. Nothing. Nothing's going to happen. If it's got 50 keV, what's going to happen? Nothing. If it has 57.5 keV, what happens? Pardon? Yes. So the inner shell electron now, suddenly this X-ray has enough energy to kick out the inner shell electron, and it's going to be absorbed. Everyone see that? Everyone's happy with that? It's suddenly got enough energy, so it's going to be absorbed. When that happens, the transmission drops right down. Because suddenly, the X-rays are now going to be all absorbed. If they've got an energy at this, if this energy for erbium, and I'm just talking about erbium at the moment, there are other materials, erbium, if you reach 57.5, suddenly all those, or nearly all those X-rays are going to be absorbed because now they have enough energy to kick out this inner shell electron. Okay? And they're going to be absorbed. They're no longer going to be transmitted. That X-ray is no longer going to get through. It's going to be absorbed by the material because it now has just enough energy to kick out the inner shell electron. And what happens when you reach 60? Same thing, but there's a little left over. Okay, so when you reach 60, what you'll see is it starts to come up again. Okay, and you start getting it up again like this. Okay, because there is now excess energy that can pass through. Okay, you've now got, if it's 75, it's 75 minus 57.5 energy, a keV that can be allowed through. Now, this is a really important concept you've got to grasp. You're going to hear about this not only for filters, you're going to hear about this for lots of things. In fact, this should be the core of what you do every time you X-ray someone. Really what you're trying to do is get that energy of the X-ray to match the K-edge of whatever you want to see in the patient's body. Because when you do that, you get maximum absorption, you'll get the clearest and highest contrast in the image. Because what it means is the bit you want to see, the kidney or the esophagus or the bone or whatever you want to see, has suddenly stopped all the X-rays. So it's going to be really white and everything else will be black. Okay, that's really what you're after. And every time you X-ray someone, that's what you should be trying to do, to exploit the K-edge of materials in the human body so that your X-ray energy, as near as we can, now we've got a broad beam, Bremsstrahlung type beam, but we try and match most of those X-rays to the K-edge of the material you're interacting with. But back to filters. We're just talking about K-edge filters at the moment. Okay? So just remember the principle. Increasing energy, the transmission goes up. However, through the erbium. However, you reach a certain point, 57.5 keV, where that X-ray can now be absorbed because it matches the binding energy of the inner shell electron. Once it does that, the X-ray gets absorbed, doesn't go through, and you get this drop in transmission, which starts to come up again once you get to 60 and 70 and so on. Now you can say to me, why? Why bother with this? Okay? What that means with your graph on your X-ray spectrum graph, what that means is that this is the graph that you're very, very familiar with. Okay, and you've got your characteristic radiation there if you're high enough, and here as well. Okay? What that means, if you stick a normal filter in the beam, what you'll get is this sort of effect. We talked about that before. If you stick erbium in the beam, you'll get, again, this sort of effect, and then it will drop at 57.5 keV, and then it'll start to go up again. Okay. And that's what, until you reach that point. Okay, yeah. Pardon? Will it drop to the bottom? In theory, if you could make sure, it's a really good question, if you could make sure that every X-ray you had in the beam was 57.5 keV, in theory, it should drop to the bottom. But I've never seen a graph with it at the bottom. So you're sort of getting me thinking. It should, but if I can add anything more to that, I will. Yeah. Okay. Now, the thing that you should notice here, which is completely different from the non-selective filters, is that you now have got rid of all this soft radiation, not all of it, but a lot of this soft radiation, but you've also now got rid of a lot of the high energetic radiation. What does high energetic radiation do to your X-ray image? Reduces contrast. Suddenly we've got a filter that not only reduces dose and reduces the soft radiation, but it enhances quality. Okay? And this is why we've been proposing for 2 decades that erbium should be used. The manufacturers simply won't put it in there because it will just perhaps lose their competitive edge. It's a much more effective filter than the others, and we've proven this in a number of different applications. But it's the principle probably that's much more important than the filter, is to understand how this K-edge works, whether it's a filter, whether it's the human body, whatever it is. What we're trying to do every time we X-ray someone is match the X-ray beam to the K-edge of the characteristic or the substance you're looking at within the body. Also, you'll notice in this beam is instead of this very broad X-ray spectrum, we've now narrowed it a fair bit. So no longer is it as crude as it was. So now it's going to be much easier to match this, not much easier, but it's going to be easier to match this to whatever you're looking at in the human body than matching all this stuff, you know? So it refines the X-ray beam spectrum effectively as well. Yeah, good.
Why doesn't the same effect happen with copper or...
Yeah, well, to be honest, it does affect, but it happens at such low energies that it's irrelevant. Because the K-edge of these two materials are very, very low. Yeah. In fact, that's your homework tonight. I think I've given you that, the kh of aluminium and copper. You can tell us next week. Okay. Any other questions? All right, kh filters I think are really important, but you've got to understand this kh thing. It's really critical to every time you X-ray someone. All right, the last thing I want to talk about then in terms of production of X-rays is just some terminology. Okay. Beam quality. If you hear the term beam quality, it's just another term for energy of the X-ray beam. Now, by the way, that graph, you will have to think about it. Some of you will have it straight off, but a number of you will have to work through this. Do work through it. If you have any issues, come back to me. Beam quality is simply the energy of the X-ray beam. Okay, tell me 3 things that will affect the beam energy. Yeah, tell me one. KVP, well done. KVP is one. Yeah. Pardon? Filter is another. Good. Pardon? There's a third one suggested is the MA. Is everyone agree with that? Does anybody agree with that? You're on your own, I'm afraid. MA doesn't work. MA is not, and remember that. MA has no impact on energy. Okay.
The angle.
The which? The angle? Yeah, the angle could have, not a major factor, but the angle could have an impact. But anode material definitely will have. Whether it's tungsten, whether it's molybdenum, how much rhenium is in there, all that will affect it. Okay, so beam quality is simply a method of, it's just a term used. When you see quality, it's a term used, it simply means energy of the X-ray beam. Okay. Half value layer we talked about, that's the thickness of a material that will reduce the intensity, remember the terms, reduce the intensity of a number of X-rays to 50%. Half value layer is the thickness of a material that will reduce the intensity of a number of X-rays to 50% of the original value. Now here's the thing just to get your mind across. Okay. Half value layer therefore reduces the intensity of the X-rays, okay, the number of the X-rays. But ultimately the half value layer is a measure of the energy of the X-rays. The thicker the half, if you've got a higher energetic beam, you need a greater thickness to half the X-rays. Okay? So ultimately the half value layer is a function of the energy of the X-ray beam. If you've got a more energetic X-ray beam, you need a thicker half value layer to get it down to 50%. So if this gentleman here, and this is important, because if this gentleman here is talking about the energy in his hospital, that the room that he's in charge of, and this lady's doing the same in her room, and how do you compare that? You know, this is a GE, this is a Philips unit, you've got an X-ray unit, you know, how do you compare the energies? You may say, well, for a 30-year-old man, for an abdomen, I use 70 kVp and I use 65, or I use 70 and I use 70. You might think, well, that must mean they've got the same energy outputs. It's really subjective. What you can do, though, if I give this fellow and say, go and X-ray with a dosimeter, go and X-ray this dosimeter at 70 kVp, and you do the same at 70 kVp, and tell me the amount of aluminium that will reduce the intensity by half, we've now got a much more accurate description of the different energies in those two X-ray rooms. The half value layer is a really good standardized measure of establishing the energy, the relative energies between different X-ray rooms. as long as the material is the same. Because you may get an aluminium filter, but some can be 99% pure, some can be 90% pure, and you've got all those sort of things as well. But there are standards about that. So I'm not going to go on about this. We'll talk a little bit more about this later on. But the half value layer is simply the amount of material, the thickness of material, that will reduce the intensity by half, but it is ultimately a measure of the energy of the X-ray beam. Beam homogeneity, heterogeneity, this is what we're showing you here. X-ray beam, every X-ray beam you will use for the foreseeable future is heterogeneous. It's got lots of energies. Okay? A homogeneous X-ray beam would look like that. Okay, we don't have it yet for general X-rays, although we can produce this in the synchrotron units. But we're hoping actually to run the first ever patient trial in a synchrotron unit in 2020. I probably told you that already. And the reason why we're doing it in a synchrotron unit for breast imaging is we can do this. Okay. But we can't do this with normal commercial units at this time. Beam, and these are all just sort of terms for beam quantity. Beam quantity is simply intensity of X-rays. How many X-rays? The number of X-rays. Okay, give me three things that affect the number of the X-rays. Which? Anodine effect, good, absolutely. Yeah, particularly on one side of the image, yeah. Another one? MA, yeah. Time, good.
KVP as well.
KVP. In fact, it's very tempting to always think KVP is energy, MA is quantity, okay? But in fact, MA is quantity, but KVP is energy and quantity. And in fact, intensity of the X-rays is proportional to the KVP squared. So KVP is actually it has a bigger impact on intensity than MA does. The intensity is proportional to the KVP squared. Okay. And this is why, when I mentioned to before the 10 kVp rule, how if doubling the MAS is the equivalent of going up on 10 kVp. So if you go from 70 to 80 kVp, that's the same as going, say, from 30 to 60 MAS. And I told you that rule doesn't work. It's a completely false rule. But that's the basis of that rule. Okay. So here's terms for the quantity of the X-rays. Fluence is the number of photons, photon fluence, and that's, of all these four terms, I think that's the only one that I ever see used. Okay? Photon fluence is simply the number of X-rays per unit area. The number of X-rays per unit area. Photon flux is the number of X-rays per unit area over time. Energy fluence is the number of energies per unit area. Energy flux, or energy flux density, is the number of energies per unit area over time. All right. And that's the production of X-rays. Now, I think you've done extremely well. I think most of you have this to understand how X-rays are produced. Yeah?
So just sort of clarify, a photon carries energy.
Photon is energy.
Photon is energy. So what's the difference between photon fluence and energy fluence?
Yeah. Energy. Photon is simply the number of photons. How many photons are in that beam? Okay. This is the range of energies of those photons within that beam. All right, so you've got a good grasp of how X-rays are produced, and you've sort of been introduced to a number of important concepts, such as anode Hall effects, filters, and so on. And hopefully some of that will be useful to your assignment in a few weeks' time. All right, let's just change now to the next lecture in this series. You will have met Peter last week, so you will have done radioactivity. So we're going to do this one, which is a bit of a dry subject, but it's important because it is so easy to be confused about different exposure and dose units because there are a plethora of them. So if this is something that radiographers are not really good at, they're not good at. You know, they're good at producing images and so on, but if you ask a radiographer, you've X-rayed someone, can you tell me give me an idea of the radiation dose that person has received? You know, often they won't be able to give you detailed information. If you went to a GP and you were prescribed a particular tablet, you'd want to know that dose so you could work out then maybe later any risks associated with that dose. Okay? However, even though we are delivering this radiation, we seem not to be good at saying how much dose are we actually delivering. You know? We're not good at it. So after this, hopefully you'll have a much better understanding that will allow you to be good at it. And I'll be giving you some numbers that give you an indication of the doses for different examinations. But you've got it because the risk, I said to you in the first class, that risk of inducing a cancer is there every time you X-ray someone. Every time you X-ray someone, you are introducing a risk that that person will get cancer. That's the bottom line. Now, the risk is tiny. It's really, really, really small. But it is proportional to dose. So if you double the exposure, you know, you have to repeat the exposure, you're doubling that person's risk. Okay? If you give a higher dose because you're careless, you're increasing that person's risk. If you use collimation like this for a finger, you're increasing that patient's risk. If you X-ray a hand, but you have the child or whatever's knees underneath the table, you're increasing that risk to the patient. Okay? So every time you X-ray someone, you've got to keep that dose as low as reasonably achievable. You will have all heard of the Alara principle by now, I'm sure many times, but it's so important, and you'll see, particularly when we get into the radiobiology lectures in this course, you'll see why that is critically important. Now, there are a whole load of dose units that we need to consider. This isn't really a dose unit, it's more of a dose concept, diagnostic reference levels, and we devote a lecture to this later on in the program, so I'm not going to go on about it much now. The bottom line is, and I said this to you before, this fellow here can go in for a chest X-ray in Royal North Shore. These are just hypothetical examples, okay? In Royal North Shore. He can then go for an X-ray in Westmead Hospital, and he will receive 23 times more radiation in Westmead than in Royal North Shore. Now, don't say to anybody in Westmead everyone gets 23 times more radiation. That's just an example, a hypothetical example that I'm giving you, okay? Well, that's what happens. We showed it in Dublin. We've showed it it's been shown in the UK. It's been shown in Germany. This is what happens. If you do a dose survey, you will be astounded by the variation of dose that's possible if the same person goes into different hospitals. It can be down to the energies, the MAS that you select. It can be down to the digital receptor. It can be down to the distance you use. It can be down to the protocol you use. There can be a load of reasons for that happening. It can be down to the radiologist that you've got who really wants a high-dose image so they can see all the exquisite detail, even though it contributes nothing necessarily to the diagnosis. So this is the fact. Diagnostic reference levels are there to provide a limit. Well, a limit's a strong word. It's a recommended level. It's there to provide a recommended level, which if you consistently, as a department, you consistently go above, then you should be asking why. It's a recommended level. They are a legal requirement in Australia. They're a legal requirement in Europe. We were the first to introduce diagnostic reference levels in Ireland when I was there. And we're introducing them here as well for a variety of different, we're looking at breasts, we're looking at CT examinations, nuclear medicine examinations as well. But they don't exist. They should have been in place since 2007. They don't exist yet in this country in a comprehensive way. So these are levels so that you can go in your hospital and say, okay, let's look at the doses I've been giving over the last month. Let's see how this now matches to this recommended level. And if you find you're consistently above it, then you should do something about it. Okay, that's how diagnostic reference levels work. Okay, and there's a whole pile of exposure and dose units. That's the aim of this class, is to go over these exposure and dose units. So I'll come back to them in a minute. Exposure indices is another one. Another concept, if you like, which I've got a lecture for. So please don't get alarmed by all these things. I will go through exposure indices later on in this program. I'll go through DRLs later on in this program. This lecture's about those things. But an exposure index, just to introduce you to it. When we used film, which isn't that long ago, 10 years ago, film was the dominant media in X-ray departments, certainly 10, 15 years ago. It was easy. If I X-rayed this lady here for her shoulder, and I gave too much X-rays, gave her too high a dose, the image would be too black. Okay? If I didn't give enough, it would be too light. We had a very, very fine latitude with exposures. Okay? We had to give the right exposure. Okay? And we were really strict, so we got really good at the exposure levels because we knew exactly what would be tolerated by the type of film or screen that we were using. And you saw this with cameras as well. You had to get, without auto exposure functions, you had to get your exposure, the daylight, the sunlight, all that stuff. You had to get it dead right. With digital, I can give an iPhone to anyone, and I can just flash away, and I'll get perfect images. My exposures will be perfect because of all this automatic exposure controls that are built in. It's the same with digital X-rays. You can now almost give whatever exposure you like, almost, and instead of this fine latitude of getting the shoulder just right, I can now give a really wide range of doses, and I'll still produce a nice image. If it's too high, really, really, really too high, maybe say hundreds of doses too high, you might get saturation, and that shows sometimes. If it's really, 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 really low, you get you don't get white. This is the problem. You don't get white because it'll still. Or when you've got a digital image and it's saying the average should be 100 and you only give it 1, then multiply it by 100. That's what digital does. So you can do that because you're just dealing with numbers. So it'll never be white, but it'll demonstrate what's the problem with really low exposures. Well done. Quantum mottle. Quantum mottle is the problem. If you remember quantum mottle we talked about, if you've got too few X-rays in your X-ray beam, you get this speckled appearance. Okay? Quantum mottle is now the limiting factor in terms of the appearance of the X-ray beam. So with film, it was easy. If a student X-rayed an image, or not necessarily a student, but someone X-rayed a patient, it came out too black, you saw it within half a second, you'd see the image, you've overdosed that patient, it's too light, you haven't given enough. With digital, we have no longer got that control. What an exposure indices or index does, it gives you a number every time you X-ray someone. If you X-ray someone, you see some sort of number on the monitor, okay, which indicates the level of exposure given. Now, I'm going to give you a lecture on how that works. It's really quite a straightforward procedure. And we're trying to get, the problem with exposure indices is that Kodak use a different number from, Fuji use a different number from, Hologic, and so on and so forth. So it's very hard to unify all these, but there is a standard now, we'll be going through that standard. But that's for later on in the program. So that's another concept you've got to be aware of. Okay, they're not units, they're simply concepts. We'll understand why each of these are important. All right. We'll just do this for a few minutes, 5 minutes, and then we'll have a break, and we'll then try and see how far we get after the break. Okay. All right. In terms of operator selected and exposure dose quantities. Sort of the operator selected quantities, and I'm just throwing it all in here so you understand all of them and how they sort of build on each other. Energy, you know. You select a KVP. You've got control over selecting the KVP. Okay? You could add a filter into the beam if you wanted to. You know? You've got control of the energy. So this is an operator selected quantity. So the energy that we often refer to is kiloelectron volts. That's usually the unit we use. Kiloelectron volts or kilovolt peak, KVP. Okay? They're simply the unit, if you like, that we use for energy of X-rays. Intensity of X-rays, we use MA, and time, MAS. Okay? And that's just what, these are operator selected quantities. This is what you're going to be choosing. Okay. Now these are what you're choosing, but they're really a very poor indicator of what's going on. As I said to you, you can have two X-ray rooms here, both saying I'm giving 70 kVp. You measure them with a filter and you find you're giving entirely different things. Okay? But that's what we will keep referring to. What did you give that patient for that wrist? You'll hear people saying, oh, I gave it 65 and 30, you know, or 65 and 5. You know, these are the sorts of things you will hear. But these are operator-selected quantities, and they have limited value. They're sort of, that's what you use, but they have limited real value in terms of what you're giving to the patient. These are the key ones, and we'll be going through each of these. Exposure or dose quantities, we have exposure, okay, and then we have dose. You see dose is written in all these three of different types of dose. Exposure refers really to air, ionization in air. Dose is much more about what you're giving to the patient, or a phantom, or a piece of tissue, or something, you know. So we'll look at each of these. That's the big distinction between this one, exposure, and the ones below it. Okay, exposure is about ionization in air. Okay. Now, okay, so they're the sort of 6 units that we talk about. I'm just going to get this energy MAS out of the way because you know all this already. So, although there's one thing we have to do. Okay, you know it's a heterogeneous beam. You know about Bremsstrahlung. You can draw the typical beam. We've done this many, many times. You can talk about filtration. We often talk about KVP. As I keep telling you, KVP is really a very poor indicator of what's going on in the beam. We will keep talking about KVP, and we'll sort of fool ourselves into thinking that patient needed 70 KVP. That means they needed that level of energy. If you're giving them 70 KVP, you're actually giving them a sort of an average value of probably close to 30. Okay, so you can sort of mix that up in your mind a little. And then you have, but how representative is KVP of the total beam? It's clearly not representative at all. So we have something called effective beam energy, which I'm not going to go into now because I think you need a coffee before you actually start getting into this, okay? So let's have a break, and I reckon it's 5:02. Let's come back at 5 past. Hi.
I email you about.
Oh yeah, thanks. I thought it was you. Yeah.
So, how?
Yeah. So what was the question again? Remind me.
Yes. I mean, you just mentioned about the risk.
About
the risk of cancer. Or
Yeah.
Yeah.
Oh,
So
yeah.
I understand the risk of cancer is the tiny risk of cancer is each time when we X-ray someone, the X-ray may be broken, the DNA change.
Correct.
Yeah, and but another thing is, I asked Carrie about this, and he said we maybe hydra the chemical in our body.
Yeah.
Yes, so the chemical change will broken or destroy
It's DNA. Yeah.
the DNA. Yeah. but the chance or one X-ray hit or broken the DNA chain is quite low.
Yeah.
So I think most of the rays is come from the chemical chain.
Okay.
So can we detect the chemical chain?
Well, the first thing is you're absolutely right, and I'm actually going to give you lectures on this. When I talk about radiobiology, in fact, the class after this one, I'm going to get into all of this about the chemical change that happens after X-rays. Yeah, we can measure chemical change because the big chemical change is about free radicals. It's the production of free radicals that happen after X-rays. That's the critical feature. So there is ways of measuring the change, the chemical change that occurs. We can also measure the amount of broken DNA. We have those sort of facilities in biology. So, but you're absolutely right. And I'm not going to go into too much of it now because I'm going to go into it in a week's time. But the bottom line is when you X-ray someone, at the X-rays we're using, not the other types of radiation types, and I'll mention that, at the X-rays we're using in diagnostic imaging, that I would say about 70% of the damage occurs through chemical change. 70% of the DNA. And not only is the chance of breaking that DNA small, it's actually the chance, even if it's broken, because DNA is 2 strands, the chance of this one breaking, it then simply repairs from the other one.
Yeah, we can use our RNA to repair it.
Yeah.
So it's not a big deal. I thought when the chemical change, the element of the DNA change, then it's a big deal.
Yeah, it is a big deal. But a lot of if it's a double strand break, then you have real problems.
Yeah.
That's far harder to repair. If it's a single strand break, which the vast majority is, much easier to repair. So even though you break DNA, the chances of it being repaired are very, very high. So it's not just about the limited opportunity for breaking DNA, it's about the ability the human body has to repair it also.
Yes, so...
But most of that DNA breakage comes from free radicals after biological change.
So what I try to find is the rate of the chemical change being recovered by our body.
Well, and what I'm going to do is I'm going to give you numbers, not this week but next week. I'm going to give you numbers that if you give a certain dose to the patient, what is the chance of that change not repairing and leading to a cancer? And I will give you precise values on that next week.
Yeah, but actually I'm interested in how we recover. I think the graph of how we recover should be something like that.
Like that.
Yeah, it should be something like that.
You mean through time? This will be time, this will be damage.
Yeah, something equal to e to the minus something.
Yeah. It's probably exponential. Yeah, that's probably right, that you get a very rapid repair and then through time.
I think probably will be exponential.
It's probably an exponential curve.
Yeah, so if we can get this and we can calculate how much one someone about the problem is the radiography actually do not know how much dose they gave the patient. But if we know that, consider if we know that, and we put it into the system, then we can know how much, and do we have a limit or upper limit of the dose?
That would kill a patient.
Will kill a patient or will have the risk.
I can. I am going to give you these numbers next week, but typical dose that would kill a patient is something like 5 to 10 Sievers. Whole body single dose. In Chernobyl, have you heard of Chernobyl? It was a nuclear power, like Fukushima in Japan. There was a nuclear incident. They established that this was what was going to kill patients. See, everything's relative because it's not actually, this won't necessarily kill patient, but there's a 50% chance it will kill you.
So if we can set an upper limit, then we can calculate this, then then there's not a risk for people to doing a little chance of risk.
There is a chance, but we know very, very little about the low doses, the impact of low doses, and this is our problem. We know a lot about the high doses because of Japan, but we don't know much through epidemiology about the impact on low doses, and this is an issue.
Yeah, so we not pretty sure how the effect of low dose will happen to us. Yeah, that makes sense, but
Yeah. But
Yeah.
we'll talk more next week.
Okay,
Thank you for the. And by the way, when you said does it remain in the body, it doesn't. An X-ray stops like this.
yeah, I know X-ray stop like this,
Yeah,
but the
yeah.
chemical will stay in
Continue.
the body.
And there is a time frame for that. Yeah.
Yeah, but I can't find it.
No, if you look in my book, I describe that. If you look in my book, in the radiobiology chapter of my book, I actually discuss the time frame for change. It's very short. The free radicals only last for 10 to the minus 7 seconds or something. Okay. Sorry. Yeah. Hi.
I'd just like some clarification on this because I understand,
Yeah.
like my understanding of it is what you drew on the board.
Yeah.
Basically that like Muhammad
Yeah.
much has been not attainable
Yeah.
at the moment. It's
Yeah.
just theoretical.
Yeah, that's right. Yeah.
So what we'd just be dealing with is the
Heterogeneous beam.
that's
That's everywhere. Everywhere every time you X-ray someone, you're going to produce this sort of beam, which has got lots of different energies in it. Okay, so that's what you're going to be doing.
so that's all I'd be writing.
Yeah.
Basically, so that's just a theoretical.
At the moment, it's theoretical.
But it's not actually something that we
No,
have.
you won't be using for at least another 10 years or so.
Just another question. So you keep speaking about the synchrotron. I'm just wondering if you know a Damien Myers by any chance?
Damien,
Myers?
I probably do. He's based in. He's obviously based in Melbourne.
Yeah.
I think I met Damien. He's
He's got like longer grey hair and
How old is he?
he'd be in his 60s.
Well, maybe I don't then. I'm thinking of someone else. I don't.
He looks like something out of Harry Potter.
Okay, the next
But
time.
he's got a lot of links to the synchrotron. He was one of
Okay,
the
well the next time I go down there, I'll look for this guy. I don't think I do know him.
Connected to like everywhere, every institution ever, because he was my supervisor.
Oh, okay.
Wanted me to do a PhD and everything.
Ah, right.
I did this.
Okay. Yeah. Okay. Well, obviously you must be a good student. You know?
No pressure.
Okay, yeah.
No, because he kept.
No, I must. What's his surname again? Damien? Myers. I must have a look for that.
He's done everything from like neuroscience through to medical imaging.
Yeah,
Now at the
okay.
moment he's looking at osteosarcopenia.
Oh
So
yeah. I
just
know.
like bone and
Yeah. And that term sarcopenia was created in this faculty.
yeah, because Gustavo Duque was
Maria Fiatroni Sings.
yeah. And now he's at the University of Melbourne. He's a chair of medicine.
Oh, okay, right,
So,
okay.
Yeah, he's basically coined the term osteosarcopenia.
Yeah, okay.
He's linked the conditions together through
Yeah.
his research.
Oh, right, okay, right,
They're all
okay.
involved in the same line.
Okay, good.
He feels like the other person in your life.
All right, okay, right,
But I just
okay.
wanted to see if you...
Okay then. Well, thanks for that. Okay. Hi.
Question about pH.
Yeah.
So, from my understanding, the X-ray gets absorbed by the filter when it has at least the same.
right. Okay, let's go. Sorry about the delay in restarting. You're asking far too many interesting questions, which are worthy of extra time. But anyway, all right. One question that came up at half time, and it's very much related to this. I keep talking about the average, that KVP, I've said many, many times that KVP is a very poor indicator of the energy, okay? And something like average X-ray beam would be something more useful. And I talk about the average X-ray beam being about a third. Now that's just a very rough rule of thumb, about a third of your KVP. So if you're actually X-ray someone with 70 KVP, you're probably, most of those X-rays are going to have something around 25 or 30 keV, okay? Now, a much more precise method is effective beam energy, okay? So if you really want to describe this beam correctly, okay, the term that you really want to use is effective beam energy. Now this takes a little bit of thinking through. That's why I thought you needed a break before we got into it. So let's do this slowly. Okay. Now, what this tries to do is attempt to represent a polyenergetic beam. This is a polyenergetic beam. There is more than one energy in there. But it tries to represent this as if it was monoenergetic. Okay? So what would be the best single energy in here that would represent this polyenergetic beam? Okay. Now, this is what happens. Okay. And as I say, it's important to sort of keep your energy levels up for the next 5 minutes. Okay. What happens is you have got people in places that have access to monoenergetic beams, okay, like in synchrotron units, or in very low-powered X-ray units that wouldn't be useful in medical imaging. But what they can do, if you've got access to monoenergetic X-ray beams, that is the ability simply to produce an X-ray beam of a single energy, okay, which, as I say, commercially we can't use those yet in X-ray departments. What we can do is take any energy we like. It could be 73. It could be 81, it could be 63, okay? We take one energy in that environment where they're producing these monoenergetic beams and calculate the half-value layer, okay? So we take 63 keV, and we find out, we X-ray, again, a dosimeter or whatever, and we find out what thickness of aluminium, for example, will reduce the intensity of that 63 keV energy beam to half. Okay? So we simply, in these places, whether it's synchrotron units or elsewhere, every monoenergetic X-ray beam has a particular half-value layer. Okay? So therefore, once you've got that, you can plot. You have a big table, and you can get it online if you like. You can get a table that will tell you the specific half-value layer for every single energy of X-rays. Anyone any problems with that? Okay. Okay. Everyone have. So say for example, this table demonstrates that through these monoenergetic beam experiments, it shows, for example, that 63 keV, and I'm just picking numbers here, gives you sort of, it requires 2 millimeters of aluminium equivalent to reduce, that is the half-value layer of that beam. So that amount of aluminium filter will half the intensity of that X-ray beam. If it's 73, you might need 2.41 millimeters of aluminium equivalent. If you've got 83, you might need 2.73 aluminium equivalent. And they have it all worked out. These people who can produce monoenergetic beams have it all worked out. Okay, that's the first step to this. Now, what you do is you go and you X-ray the dosimeter with your conditions at a particular kVp or whatever, okay, in your X-ray room, and you find out. So you're using what you may have chosen a beam that looks about this, and you chose something like 65 kVp. Okay. You simply find the half value layer for your beam. Okay? And if your half value layer turned out to be 2.41 millimeters of aluminium equivalent, what energy is it? Just look it up on the table. And you simply got 73. So that means that is your effective beam energy. That would be your effective beam. That's a very high effective beam energy. It's not realistic. Yeah.
Just qualifying, this is only with like those calculations, right?
Yeah.
Like effective beam energy has no other purpose.
Yeah, you're absolutely right. But ultimately, if you know the purpose it has is if you are choosing a say 70 kVp to X-ray someone's shoulder, okay. 70 kVp is such a poor indicator of what's going on in that beam that this really, if you really wanted to know what's going on in that beam, an appreciation of the effective beam energy would allow you to say, well, actually, most of those X-rays, if I could describe this as a monoenergetic radiation, it's only down about 25. And then that allows you to work out, well, I know that the K edge of iodine is this, so therefore I should be a little bit higher to maximize this. That sort of thing, that's where it's used. Now, I'll just go over that again because people do get a bit confused, yeah. Yes, you can do that. You can't change the half value. You can change the filter. You can add to the filter. No, these values are written in stone. So these are done, scientists have done this and they've proven to you, they've said that the half value layer of an X-ray beam at this sort of KeV is that.
If you wanted to change your KUV value, say you were currently working with something that was around 63 and you wanted to change it to 83, how would you implement that?
The KeV? Yeah. Well, you see, these are not things you're doing. The only thing you can do, so these are tables that someone away from you has produced. Okay, so they're like a reference table. Okay, so when you go into your X-ray room, what you can do is all you can do is work out the half value layer of the beam that you are looking at right now. You can't, well, you can change it if you like, but under a particular, if you were X-raying meat for an abdomen, you set 70 kVp and 30 MAS, that's what you're going to set. Then you would check the half value layer of that, and then you can say, well, I gave him the equivalent of 63 keV. And then if you gave me a different exposure, you'd then re-look at because your half value layer would change if your energy has changed. Does that make sense? Okay. So what you're simply doing is you're simply working out in your unit the half value layer, whatever conditions you've decided for a particular exposure. Okay? Once you've got that half value layer, you then run over to this table and find the half value layer that matches, and you go across and you find your effective beam energy. Okay? And that's as simple as that. Okay? But you'll find that effective beam energy is usually close to about a third of the kVp. I should say it's very much a theoretical concept, but by having an understanding of it, you really do start to appreciate how poor kVp is at describing the energy of the X-ray beam. And it's very close usually to, if you could calculate the average X-ray beam, it's usually pretty close to it. Any questions or queries on that? It'll, again, yeah. Yeah, sure. Okay, so if you can imagine, someone somewhere has produced in a synchrotron unit a whole table of energies of X-ray beams and half-value layers. Okay, so it's got a list of down to 0.1 of a millimeter, 0.01 of a millimeter. It's got a whole list of half-value layers. Okay, so I've only put 3 here. There'll be hundreds of them. Okay, so what you do is you go to your X-ray unit for a particular. So you wanted to compare, for example, your beam with this guy's beam, and you set the same thing, 70 and 30 MAS or whatever, okay? And you work out the half-value layer. So the half-value layer is the thickness of filter aluminium, for example, that will reduce the intensity by half, okay, for 70 and 30. This guy will do the same, okay? And your half-value layer might be 2.1, his might be 2.4. But instead of now saying, well, we're giving the same because I've given 70 and 30, he's given 70 and 30, what you will be saying is, you'll be finding your 2.1 or whatever I said it was, and you'll be saying 2.1 millimeters of aluminium equivalent actually gives me an effective beam energy of 66, whereas this guy's giving 2.4 and he's getting 73. So now we've got a much more honest appraisal of the different energies. So what you're doing is you're simplifying the half-value layer in your unit, going to the table, finding that half-value layer, and then just pulling up the effective beam energy that matches it. Yeah. 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 It is pretty similar. So I was suspecting a more complicated question, and I said, okay. So, okay. Righto. Okay. All right. Let's move on. I think that you've probably got that, but think about it. It takes a little bit of thought. So in terms of energy, we're coming back to these operator selected quantities. We can choose KVP, effective beam energy, mean beam energy. Okay, you'll find we constantly use this KVP, but I hope by now you realize just what a poor indicator of energy that actually is. Okay, the other one is, and I'm not going over this again, we've talked about this before, is the operator selected quantities for intensity. We deal with MAS, but things like photon fluence, the amount of photons per meter squared, for example, is a much better indicator of how many X-rays are in that beam than simply the MAS. And don't forget, the manufacturers fiddle with the MAS all the time, you know, because they know that, for example, your tungsten is wearing down. They know that you're getting, remember, the sort of tungsten vaporization across the glass, so the output's going down. So what might have been 3 MAS in 2010 when you bought the machine might in reality be more equivalent to 1.5 MAS in 2018. So what they do is they up the MAS to make it the same, okay? So you don't see this, so you don't visualize all these changes. So just be very wary again of MAS being a very useful, being a useful sort of indicator. Some people, when they're talking about exposures and how much radiation the person's getting, as this lady told me at halftime, she sometimes multiply the KVP and MAS to give you a number. Okay, you can see how, you know, how it's rough that is. You're using KVP and you're using MAS, which the manufacturers have fiddled with. So you just have, you know, it's some indication, but it's not a very valuable one. Okay, so that's the operator selected quantities, which you know well. You know about energies now, and you know about MAS. Let's move to something you might be less familiar with. Now, these are not operator selected things. These are actually measurable things that you can actually, they're much more objective, measurable things. Exposure, as I said to you, is simply about ionization in air. Okay? So in other words, if you've got an amount of air, okay, you've got you can simply have like a box of air, and that's how. Have you all been in X-ray departments at this stage? Anyone not been in an X-ray department? Okay. Have you come across DAP meters where they record the exposures or the doses to the patient? Yeah. You haven't been in clinics yet. Just the ones down here, is it? Okay, thank you. Okay. Well, what you'll find is we record doses much more than we used to, even though they're not used very effectively. That's not coming up. Okay, so what you have an X-ray tube, and now by law, you're supposed to have, before you reach the patient, up here somewhere, you've got something called a dose area product meter, a DAP meter, a dose area product meter. Now we'll talk about this maybe a little later, if not today, tomorrow. Okay. And what this does, it indicates every time you X-ray someone and you get your image on the screen, it'll have a somewhere it'll record a number, okay? And that's often a dose area product meter. It's most used for fluoroscopic examinations like barium studies or angio studies or whatever. It's a dose area product meter, but I'll come back to that. Don't worry about the meter. We'll talk more about this. It's the concept I'm trying to explain. How that simply works is that this box that you can see here simply consists of air. It's a volume of air. So when you X-ray this box, you're going to get the production of ion pairs. You're ionizing the air. So by ionizing the air, you break the air up into negative and positive ions. Once you do that and then apply a charge here and here, you get a measure of the level of exposure that has taken place. Because obviously if you've got lots of exposure, you're going to have lots of ion pairs, you're going to have more charge difference between this plate, and then that's a measure of your exposure. Okay? And that's simply how it works. It's about air being ionized and then measuring the number of ionizations that has taken place. Okay? And that's exactly how this DAP meter works. What it's doing is measuring the amount of ionization in air. So it's the ratio of charge that's created as a result of those ionizations, the ratio of that charge in air to mass of that air. So this is a fixed unit. We know the mass of the air. We then measure the charge, and we've got our ionizations. Yep.
So if you just used up some of those X-rays to ionize the air, ultimately that's going to affect what comes out.
Yes.
And the patient.
Yes. Yeah, it's going to reduce. It's going to absorb some of the X-ray. Now, because it's air, it's going to be pretty small. Obviously, these things are usually made of thin plastic walls, so the level of attenuation is pretty minimal, but it's definitely there. Yeah. The other thing to be aware of, and we'll talk more about this, is that it's not measuring the dose to the patient at all. It's only measuring what's leaving the X-ray tube. But we'll talk more about that. But you can see how it's a cool thing that can be in there. Every time you X-ray someone, it's clearly transparent, so you don't see any of this, completely transparent. But it certainly means that every time you X-ray someone, you've got a dose. You've got an indication of dose, which may not be perfect because it is just simply measuring what's leaving the X-ray tube, but it's certainly better than KVP multiplied by MAS. So this is all fairly straightforward. So exposure, when you hear that, we talk about exposure loosely, but strictly speaking, exposure means the ratio of charge in air to mass of air. That's what exposure actually means. And here we've got the SI charge over mass is exposure. The SI unit is the coulomb per kilogram. Okay, so let's work through these units now, and that's what we'll do. We probably won't get into the sort of the dose meters, and I don't worry about that. We can talk about that next week, but let's talk about the doses and the dose units. So what we've got here is exposure, and the SI unit is the coulomb per kilogram. Now, that's not used much. It's not used much, okay? What you'll often see used instead is something called Röntgen, okay, to honor the great fellow himself. And 1 Röntgen equals 2.58 times 10 to the minus 4 coulombs per kilogram. Röntgen's the old unit. They use Röntgen's a lot in the US. But just so for exposure, you can use Röntgen or Coulomb per kilogram, and that's how they equate to each other. Okay, any questions on exposure? Exposure is simply ionizations in air. Okay. And it's neat for giving us very rapid, ongoing doses rather than every patient coming in and me having to put something on the patient to measure the dose. Yeah?
Is measuring this exposure with that DAP meter, that's different to measuring the dose?
It's this is a step before the dose, yes, yeah. But you can, there is actually ways, because it's not, whilst they are distinct, they're still dependent on each other. They're not going to be independent of each other, because what's happening here is clearly going to be related to what happens to the patient. Yeah. But it's not the same. Yeah. Okay, let's move on to dose. Notice the difference. Dose is about energy deposited within a volume of tissue. It's no longer about ionization of air. It's about energy deposited within a tissue, divided by the mass of that volume. And this is the first of the 3 doses you'll come across. And you'll see why each of them, as we progress, why the next one is necessary and so on. So this is absorbed dose, amount of energy deposited within a volume of tissue. Exposure is related to, okay, let's leave that for a moment. The unit is the gray. Okay, you'll hear that term many times, far more than Röntgen. You'll hear gray many times, milligrays, centigrays, and so on. And it simply relates to the amount of energy deposited within a volume of tissue. But coming back to this lady's question a moment ago, exposure is still related to this because it could be absorbed dose in air. This volume of tissue, in theory, this could be a volume of air as well. Okay, so it's the energy deposited as opposed to the number of ionizations. Okay, and because of that, if you know the mass, you can then work out the equivalent between exposure and absorbed dose, and that's the relationship. Okay, so they're just 2 simple concepts you've got to remember. The first is exposure, ionizations in air. Second is absorbed dose, energy deposited within a volume of tissue, or even, you can say, volume of air. Now, you could say to me, well, okay, well, that's it. We've sorted it out. Okay, we've got the amount of energy now. So we x-ray someone. How much energy have we deposited within this patient? Okay, why do we need something else? We do need something else, and that something else is something called dose equivalent. Okay, remember the units you've learned so far. You've learned Röntgen, you've learned Gray, you've learned Coulomb per kilogram. The problem with absorbed dose is that it doesn't take into consideration the type. It only tells you how much energy is being deposited. It doesn't tell you about the impact of that radiation on the body. It doesn't tell you the effectiveness of that radiation. Let me give you an example. There are different types of radiation. So you've got X-rays, which you now know quite a bit about. You've got gamma rays, which you know quite a bit about. Then you've got things like beta particles, which are no longer, it's a particle. It's no longer, remember, X-rays and gamma rays have no charge. They have no mass. Okay? Beta particles have both. You've got then alpha particles. You've got neutron radiation. A whole load of different types of radiation. A whole load of different types of radiation. Now, for example, an alpha particle, if I had X-rays here, and I X-rayed this tissue, the X-rays, almost all of them would go through this tissue. Okay. If I had alpha particles of radiation, the alpha particles would be absorbed by this tissue. So you might be inclined to think, well, that's pretty good. You know, a piece of tissue, those alpha particles cannot be damaging because a piece of tissue is able to absorb these types of radiation. However, what that means is that the alpha particles have come in and been completely absorbed within a tiny amount of depth, which means the level of effect on this tissue is huge. Okay? And that's known as linear energy transfer. Okay? So what we've got is if you've got a volume of tissue, say a patient, okay, an X-ray comes in, or several X-rays comes in, it might deposit a little bit here, and some of the X-ray might escape at the end. Okay? If this is an alpha particle, what it does, it comes in, but everything is deposited here, having a massive effect on the body. Instead of this nice gradual impact on the body, it has a massive effect on the body. Okay? Okay? So all the ionizations happen here. This type of radiation, we said, has high LET, high linear energy transfer. Okay? Because it transfers all of its energy over a very small area. X radiation is known as low LET because it spreads its radiation through the depth of whatever you're radiating. Now, story that illustrates this is that in 1930 there was a company in Germany that made luminous clocks. And you know, you've all seen luminous clocks, you know, they glow in the dark. And this company decided that the best way of getting maximum luminance is to get an excitable material, some material that's going to glow in the dark, and attach a radioactive substance to this material. I can't remember, it was some sort of uranium-based material. I can't remember which one they used. But anyway, it was an alpha emitter, okay? So it was really, really good at glowing in the dark. You know, you had this really extremely bright clock in the dark, which had this luminescent material and this alpha emitter banging into it, giving it really great luminescence. Then people started to die in the factory. And they died of horrible diseases. They had cancer of various bones, fractured femurs, they had necrosis of the jaw, they had lots of horrible diseases. And the manufacturer said, it can't be anything to do with what we do, because we're using an alpha emitter. And this tissue will stop an alpha emitter. Therefore, it can't be doing any harm to the patients, or to the people working in the factory. What it was doing was, what happened in practice, and what they're saying sounds quite right. You just get something you've painted, it shouldn't be able to get into you, because if anything, it's going to be absorbed by the stratum corneum of the skin, which is a dead layer of skin, you know. What they were doing was, when it came to the tricky numbers, like the 3s and the 5s and the 8s, what people were doing was they'd get the brush, and they'd lick the end of the brush to get a nice sharp sort of edge so they could paint these numbers on really, really well. Once they were licking the brush, then the stuff was being ingested, it was then being absorbed, it was reaching bone marrow. Now it's in intimate contact with stem cells and so on in the bone marrow and creating these dreadful, dreadful diseases because it was depositing this massive amount of energy into bone and so on and creating these horrible effects. That's what high LET radiations do. We don't use alpha particles in medicine at all because they are pretty ferocious things. I can't see much use because there's no penetration through the patient anyway. So what this all means is that different radiation types have very different effects. And in fact, an alpha, and we give each radiation, therefore, a weighting factor dependent on its effect. For alpha particles, we give a weighting factor of 20. So what that means is 1 gray of absorbed dose equals 20, I don't know if it says it there, 20 sieverts of dose equivalent. So 1 gray of alpha particles equals 20 sieverts of dose equivalent. For X-rays, the weighting factor is 1. So that means that absorbed dose equals dose equivalent. So we've got it easy. Because in other words, that tells you that alpha particles is 20 times more destructive than an X-ray or a gamma ray. Beta particle has a rating of a weighting factor of 2. Neutron radiation somewhere between 5 and 10, depending on the energy. But the bottom line is just remember these extremes. X-rays have got 1, alpha particles have got 20. Well, that means that if you know the absorbed dose, you automatically know the dose equivalent because it's the same. And this is why people will interchangeably use dose and sievert. Because if you know you interchangeably use gray and sievert. Because if you know the gray from absorbed dose, you automatically know the dose equivalent for X-rays. Okay? But the dose equivalent needs to be there because if you're using other types of radiation, you wanted to know the biological effect, which is ultimately what we're trying to do. We need to know this equation. Okay? It's joule per kilogram. The SI unit is joule per kilogram. Sievert is 100 rem. Now, something I must have skipped at the bottom of the slide previously. Yeah. The unit is gray for absorbed dose, and 1/100th of a gray is a rad. So let's just work through this. Absorbed dose is gray. 1/100th of a gray is a rad. So the Americans will refer to rads all the time. Okay, rads and grays all the time, but particularly rads. Okay. With the sievert, the 1 sievert equals 100 rem. So a rem and a rad are equivalent as far as X-rays are concerned. Okay. So you've got absorbed dose, grays and rad. You've got dose equivalent, which we need to know about because of the different types of radiation, and we have sieverts and rems. You'll often hear us refer to this in X-rays. Okay? If you ask how much dose has a patient received, we almost always talk about sieverts. 10 millisieverts, 1 millisievert, 20 millisieverts, or whatever. Okay, remember it's millisieverts. By living this year, you will have received 5 millisieverts just by radiation coming from space and what you're eating and so on. Okay, so the last dose that I want to tell you about, and then we'll finish, is, and you can say, well, why do we need yet another one? We've got absorbed dose, we've now got dose equivalent, takes into consideration the effects of the type of the radiation. The last one we've got is effective dose. So the weakness with absorbed dose and with dose equivalent so far, we haven't considered which parts of the body you're irradiating. If you irradiate someone's chest with hypothetical 1 sievert of radiation, and you X-ray their gonads with 1 sievert of radiation, same dose equivalent, same absorbed dose, you'll get a profoundly different effect. Okay? So what effective dose does, it takes into consideration the radiosensitivity of the organs that you are irradiating. It takes into consideration the radiosensitivity of what you're irradiating. For example, we know, and we'll get into radiobiology in a couple of weeks, but we know that the gonads are more sensitive than the liver. We know that breast tissue is more sensitive than brain tissue in terms of radiation sensitivity. We know that children are more sensitive than adults. We know that individuals in utero are more sensitive to those individuals who have been born. You know, so there is a whole range of different factors that will influence the impact of the radiation. Because ultimately, when you measure dose, we're not measuring dose for dose's sake. We're measuring dose to try and work out the impact of this radiation on this individual. And to do that, we've got to have effective dose. Because what effective dose is, it takes into consideration your absorbed dose, It takes into consideration the type of radiation. It takes into consideration the organs that you have just irradiated. And that's ultimately much more useful than anything else. If you ever try and publish a paper on doses, you'll be expected to use effective dose. It's the most useful indicator in terms of trying to understand the impact of radiation. Some people, few people really don't like it, and we can discuss that as well, but the vast majority of people still want to use effective dose as the most useful indicator. All right, so the weakness of dose equivalent doesn't take into consideration the parts of the body you irradiated. So it takes into consideration that breast, for example, is the most sensitive part of the body. It has the highest ranking in terms of sensitivity within the body. It gives each organ a weighting factor. So depending on whether you've x-rayed, if you do an abdomen, it'll consider that you've x-rayed the kidneys, you've done a bit of the liver, part of the spleen, intestine, and so on, and it will give each of those a weighting factor. You then work out the dose to the individual organs. So you've irradiated my abdomen. You work out from that irradiation how much dose, what proportion of dose will have gone to the liver, to the spleen, and so on. You then multiply that by your weighting factor for that organ. You add it all together, and you've got your effective dose. That's how it works. So what you do again, you x-ray someone, you work out, and they've done this already for you, so you don't have to do all these calculations. You basically x-ray someone, you work out how much dose will have gone to each of the different organs. You then multiply that dose to the kidneys, for example, by its weighting factor, and to the breast by its weighting factor, and so on. You then, the results of all that, you add together, and you get one value, which is your effective dose. And that's how it works. And that slide simply just sums all that up, and you end up with the effective dose, which is the CVET. Okay, so let's just, there is a little bit more to this, but we can finish this next week. So let's just wrap up what we know about these doses. We talked about the operator values, which I'm not too concerned about. KVP, MAS, you know about those. Then we moved on to exposure, which is simply ionizations in air. Then we moved to dose, which is energy deposited in a volume of tissue, and there are 3 units you've got to consider. Absorbed dose, which is simply how much energy have you deposited. Effective dose, which takes into consideration that energy deposited, but also the type of radiation you're using. For X-ray, it's very easy because it's got a quality factor of 1. So whatever you give in absorbed dose equals your effective dose. But then we've got to consider the organs you're irradiating, because your effect will be profoundly different for a pelvis exposure compared with a chest exposure. And that's what effective dose is about. Any queries or any questions on any of that stuff? Yep.
Sorry, could you just go over the units for dose?
Dose equivalent.
Yeah, so absorbed dose.
Yeah.
The grey, effective dose.
Yeah, okay. So for absorbed dose, the unit is gray, but 1/100th of a gray is known as a rad. Okay. Okay, that's the commonly, I'll go back to those slides. Okay. Okay. And the old unit, and there is an equivalent between the Röntgen and the gray, and you can see that there. Okay, so for absorbed dose, you need to think about gray and rads. For a dose equivalent, you need to think about sieverts and REMs. Never used a REM in my life, but the Americans do use it. Okay. We talk about millisieverts. So let me ask you just to make sure you've understood that. If I said to you for a CT, which would be a reasonable one, a CT chest would be giving 10 millisieverts, how many rads, how many REM would that be?
Because the REM was the same as
Yeah? So 10 millisieverts would equal how many REM? If a REM is 1/100th of a sievert, so to get your head just twisted about, yeah. So if a REM is 1/100th of a sievert, how many millisieverts in a REM? Yes, 10. Because if it's a millisievert, then there must be a So if you've got a sievert, that equals 1,000 millisieverts, okay? And a sievert equals 100 rem. That means there must be 10 millisieverts to 1 rem. Okay? That's what that means. So that's basically. I never use the rem. You know, we will use sieverts and millisieverts nearly in most of our discussions. Okay? And classic examples, as I say, CT lungs would be 10 millisieverts, effective dose. A pelvis would be about 1. Just a pelvis X-ray would be about 1. A chest would be about 0.1. Okay, but we'll talk more about doses later on. So just to go over that. So absorbed dose is Gray and Rad. Dose equivalent is sievert and rem. And thank goodness, effective dose is sievert and rem also. By the way, we haven't talked at all about radioactivity, which is something that Peter will have talked to you about. If you talk about radioactivity, you're talking about curies and becquerels. We don't have to worry about that. Okay. Any other questions? Yeah. Yeah.
So the first topic, the radiation dose assessment, is that made before the like taking X-ray before that, or assess, or you kind of take a guess how many exposure the patient going to be exposed, or is the measurement after the exposure?
It's just about, it's the whole thing. Is it useful? You know, is dose assessment useful? And you'll talk about the different methods of dose assessment. So you can talk about these things we talked about today. You talk about DRLs, which we haven't done yet. But it's the whole thing. It's the whole thing. You know, is dose assessment, is it important or isn't it? Why should we bother? You know? So it's not really, whilst you should show a knowledge about these different types of unit, you don't have to necessarily demonstrate, you know, loads and loads of information on different units and so on. So yeah. Yeah. Yeah, for sure. All those sorts of things would be useful. Yeah. But I can't remember the title of that assignment. I think it's about, is it dose assessment is an unnecessary exercise, or what is it?
Yeah, unnecessary.
Yeah. So it's basically it's justify why it's, you know, obviously to justify why dose assessment is really important, because it's linked to the risk, and then also how we would do it and so on, and we want to keep the dose as low as possible. We can't do that. We don't know if we're doing that unless we measure the dose, and these are ways in which you can measure the dose.
Okay. But by the way, how do we calculate those?
How you calculate this? I'm going to show you that next week. I'm going to tell you that next week.
Yep. So we calculate those with KVP and MAS?
No, never with KVP or MAS. You calculate the dose through. So say I X-rayed you. I want to know the dose that I've delivered to you.
Yeah.
Okay. I can do this in a number of ways. I can do this by. I could do this by measuring the anesthesia, and then I can convert that into a dose. Or if you're here, if you're the patient here, I can put a device on you that measures the radiation.
So we can directly measure it.
Yeah.
And is that related to the KVP or MAS?
Yes, for sure. If you give a higher KVP or higher MAS, you'll increase the dose.
What is the expression related to the dose, in my body?
Yeah.
So it works in air here, so
Yeah.
the energy, maybe the dose will spend here. So I mean the distance between
Yeah, between here and here could affect the level.
Yeah.
Absolutely. And this is why I said right at the beginning, this only measures what's coming out of the X-ray tube. Translating that to what's actually getting to the patient is a tricky science, but if you look at the papers, what they'll show you is there is pretty strong correlation between the dose calculations here and the dose calculations here. That they do agree pretty well, even though there are weaknesses for the reasons you say. The gap here could change. Like for example, if you move further away, if my X-ray machine is here, okay, and I X-ray you here, okay, and I come back with the X-ray machine to double the distance, okay, the amount of X-rays leaving here must multiply by 4 to reach you to get the same level reaching you, which means that this doesn't take that into consideration, you know. So this is why this is you only use it under prescribed circumstances. It tells you what's leaving the X-ray tube. If you know this distance, then you can sort of work out what dose the patient has received.
So, is the dose here angle related to the square law and the distance?
Yeah, for sure.
And what I think is when it passes through the air,
Yeah.
will it absorb by the air?
Not much. There will be some ionizations going on, but not a lot, you know. There will be some, and there will be some absorption, but air's not a good, like look at the lungs. If you X-ray the lungs, they appear black. You know, the air doesn't absorb X-rays well.
So, actually we can just ignore it. So,
We can't ignore it, but we
can just think it's a less.
it's not important. It's not important. Yeah.
Is the air trapped inside the box?
No, it's trapped. It's trapped.
Well, how does it? Is it always on?
Yeah, well then.
It keeps getting lost in the X-rays.
Yeah, it keeps getting ionized, but then the air will the ion pairs will come together again. You know, from it. Yeah. Now, it's a good point. Do these things leak air?
Or do you leave it until it?
What happens normally is that when the manufacturers come, there's ways of calibrating these machines to make sure that you give a particular exposure, you get a particular reading. And if that should start fluctuating or whatever, then they're going to have to do something with it, you know, whether it's adding more air or whatever. You know.
My question was a real quick question.
Yeah.
Because we mentioned computers and that sort of stuff. That information came from a textbook. And the guidelines you say from current research and textbook.
Occasional textbook use is fine. Occasional textbook use is fine. But you'll find there'll be some literature there as well. There's a blend.
Cool. That's what I wanted to know.
That's okay. Yeah, that's all right. Righto. Hi.
I don't understand why. Actually, I think that effective dose is not used because everyone is different. Like
Yeah, and that's one of the reasons why some people don't like effective dose, because it's different. Effective dose for you could be very different from a small child, and we are aware of that, and that's one of the issues. But if you look at the risk calculations that which I'll talk more about later on, they do take into